Welcome to This Explainer. I'm your host, and today we're decoding the reality of Cambridge physics. We are embarking on a journey from the observable, everyday phenomena in our sky straight down into the invisible physics that govern our entire universe. We're going to explore the breathtaking mechanics of our solar system, the cosmic clockwork, and uncover the fundamental patterns and rules that keep everything in perfect perpetual motion. There is no guesswork here, only patterns. So let's jump right in and learn to see the code.
Just look at the sheer vastness of this solar system, with that magnificent visiting comet cutting right across the dark void. It kind of makes you ponder the hidden rules that keep this giant cosmic clockwork ticking, doesn't it? Like, what forces actually dictate the path of that comet? Why does it travel exactly the way it does? Today we're going to decode those hidden physical rules so you can confidently tackle any question thrown your way.
Here is our roadmap for today. We're starting with the familiar sky above us, the Earth, Sun, and Moon. Then we'll zoom out to the broader solar system, explore the invisible strings of gravity, visualize the true shape of orbits, and finally, calculate actual cosmic speeds. Let's get to it. Section 1. Earth, Sun, and Moon. The local view. Let's start with what we experience every single day. Now, what's absolutely crucial about this is how it illustrates the rhythm of our lives. We all know the Earth spins on its axis, which gives us day and night, right? But it's this wider journey, the 365.25-day orbit around the Sun, coupled with that highly specific 23.5-degree tilt of the Earth's axis, that actually causes our seasons. Examiners love testing this distinction, so lock it in.
Let's trace this journey. Because the Earth is tilted, different hemispheres lean towards the Sun at different times of the year. In June, the northern hemisphere is tipped toward the Sun. Because of this angle, it receives longer hours of much more direct sunlight. That solar energy is less spread out, making it hotter, which gives us summer. At the exact same time, the southern hemisphere is tipped away. It's receiving more spread out energy and fewer hours of sunlight, causing winter. Fast forward 6 months to December, and the roles completely reverse. It's an incredibly elegant balancing act of light and heat.
And while the Earth orbits the Sun, we have our own companion. The Moon takes roughly 27.5 days to orbit the Earth. But remember, it's just a rocky spherical body. It produces absolutely zero light of its own. What we're actually seeing when we look up at a waxing gibbous or a waning crescent is literally just the Sun's light reflecting off that rocky surface. The phases change simply because our viewing angle from Earth changes as the Moon continues its monthly journey around us.
Section 2. Our solar system, the wider neighborhood. Now before we continue, subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's zoom out and observe everything else trapped in our Sun's massive gravitational pull.
You know the story of Pluto, right? For the longest time, we considered it the 9th planet, but our understanding of the neighborhood evolved. Under the rules set by the International Astronomical Union in 2006, to be a planet, an object must orbit a star, be spherical, and have enough gravitational pull to clear other objects out of its orbital path. When astronomers found other large icy bodies out near Pluto, like Eris, they realized Pluto hadn't cleared its neighborhood. So it was officially reclassified as a minor planet or dwarf planet. It still orbits the Sun, it just doesn't have the gravitational dominance of a true planet. And this perfectly illustrates the diverse layout of our system. Notice the sharp structural contrast here. We've got the inner planets, Mercury, Venus, Earth, and Mars. They're small, dense, and rocky. But as soon as we move past Mars, the landscape changes completely. We hit the outer planets, Jupiter, Saturn, Uranus, and Neptune. These are massive, swirling, huge balls of gas.
So how did this specific layout happen? Well, billions of years ago, the solar system started out as a nebula, a massive, swirling cloud of hydrogen gas and dust left over from exploded older stars. Gravity pulled the vast majority of this mass together into the center to form the Sun. The remaining dust and gas flattened out into a spinning ring called an accretion disk. Inside this disk, a process called accretion kicked off. Gravity pulled particles together, forming rocks, then boulders, and eventually our inner planets. The intense heat of the young Sun essentially pushed the lighter, gaseous materials further out into the much colder reaches of space, where they eventually clumped together to form those massive outer gas giants. But hey, planets aren't the only things in this disk. We also have asteroids and meteoroids, which are basically rocky debris mostly found hanging out in the asteroid belt between Mars and Jupiter. And then we have comets. Comets are a completely different ballgame. They're giant snowballs of ice, dust, and gas that travel in from the freezing outer edges of the solar system on highly irregular orbits. As they get near the heat of the sun, they start to vaporize, leaving a beautiful trail of dust and gas. And here's a highly testable fact. That glowing trail isn't just trailing behind the comet's movement like a wake in water. It's actually being pushed by the solar wind, meaning the tail always points exactly away from the sun.
Section 3. Gravity and orbits. The invisible strings. What keeps all these massive bodies from just flying off into the endless void? Gravity.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's analyze this data table to see how gravity shapes our neighborhood. Notice the clear pattern here. Look at the relationship between a planet's distance from the sun and the duration of its orbit. Mercury, sitting super close at just 58 million kilometers away, completes an orbit in a blistering 0.2 Earth years. But then look down at Neptune, practically in the deep freeze at almost 4,500 million kilometers away. It takes a massive 165 years to complete one single orbit. The further away you are, the weaker the sun's gravitational pull, meaning the planet travels slower on a much longer path. And look at surface gravity. Jupiter, a massive gas giant, exerts a crushing 26 newtons per kilogram. That's more than double Earth's 10. Mass dictates gravity, and gravity dictates the cosmic dance.
Section 4. The physics of ellipses. Let's look closer at the actual shape of these orbits, because contrary to popular belief, they are not perfect circles.
Planetary orbits are actually slightly squashed circles called ellipses. The amount the orbit is squashed from a perfect circle is known as its eccentricity. And crucially, the sun isn't perfectly in the dead center. It sits slightly off to the side at a point called the focus. Take Mercury, for example. It is the most elliptical orbit of all the planets, swinging from 46 million kilometers away at its absolute closest, all the way out to 70 million kilometers at its furthest. As an object passes near the sun at that close focus point, the gravitational force pulls it in tightly and causes it to seriously accelerate. Now pay close attention, because this creates an incredibly elegant exchange of energy, and it's a massive pattern to recognize. Because there's no air resistance in space, a planet or comet's total energy remains totally constant. It just trades back and forth between kinetic energy, the energy of motion, and gravitational potential energy. When a comet is at its furthest point from the sun, it's moving at its slowest, right? So it has maximum gravitational potential energy and minimum kinetic energy. But as it falls back toward the sun, it accelerates. By the time it whips around the sun at its closest point, it's moving at its absolute fastest. Right there, it has maximum kinetic energy, and its gravitational potential energy is at its minimum. It is literally a perpetual pendulum swinging through the vacuum of space. Section 5. Calculating cosmic speeds, mathematics of the void. Now it's time to translate these beautiful physical laws into the mathematical equations that actually let us measure this clockwork. Let's break down the formula for calculating average orbital speed. The distance a planet travels is roughly the circumference of a circle, which we calculate as 2 times pi times the orbital radius, or r. The time it takes to complete that single lap is the orbital period, denoted as a capital T. Therefore, speed equals distance over time. V equals 2 times pi times r divided by t. This one equation unlocks our understanding of the true scale and speed of our universe.
All right, let's do a quick interactive challenge. How fast are we moving right now? We know Earth's average orbital radius r is 150 million kilometers. We know the orbital period t is exactly 1 year. If we want our answer in kilometers per second, we just convert that year into seconds. So 365 days times 24 hours times 60 minutes times 60 seconds, that comes out to about 31.5 million seconds. So we plug that 150 million kilometer radius into 2 times pi times r and divide it by those seconds. Do the math in your head.
The math reveals a completely staggering truth. Right now, as you sit watching this explainer, you are hurtling through the vacuum of space on a rocky sphere at an astonishing average speed of 30 kilometers every single second. 30! It's a mind-bending reality hidden just beneath our everyday perception. Finally, as we look past our own solar system to the outer edges of the galaxy, distances become unimaginably huge. Calculating speed in kilometers per second just doesn't cut it anymore. We have to introduce the light year, the ultimate cosmic measuring stick.
It is simply the distance traveled by light in one single year. Just for context, the very next nearest star after our Sun is Proxima Centauri, sitting 4.2 light-years away. To grasp these incredibly vast distances, astronomers rely on that exact same foundational speed equation. Knowing the speed of light is a constant 300 million meters per second.
So, the crucial takeaway is this. From the tilt of the Earth causing our seasons, to the gravitational pulls forming accretion disks, to the kinetic energy exchanges whipping comets around the Sun, the universe operates on a breathtakingly precise set of physical patterns. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.